already several times, so that was indeed his name. So from that you understand that he is one of the, when it comes to machine learning and statistical physics, and in his case also neuroscience and links to biology, that he is one of the big authors in these fields. And we are looking forward very much what the lecture this year will be about.
Okay, thank you very much. Thank you all for coming. I want to start with introductions about the general themes that I would touch upon in my lectures. But first, as a matter of introduction, let's talk first about what would be the goals of theory. Theory, I mean, of deep learning. Okay? What a theory of deep learning should explain or would like to explain. So, of course, the long list, but I just mentioned here lists a few of them. Not a particularly important order. So, for instance, memorization or memory capacity. How much random information, random data a network can store. So that's memory aspect. Expressivity. What classes of functions a given architecture can express or can approximate. Then the whole important questions of generalization. And here we have already, your experts about over-parameterization issue, regularization, inductive biases, etc., etc. This is the core of theory of deep learning to explain. Then issues of dynamics, learning dynamics. And then among other issues, which I list here, is understanding the representation that emerge, latent or hidden representations that emerge after or during or after learning. How is the data represented throughout the lecture beyond performance? This is the performance, this is the output, this is what happens inside the network. And finally, a relation to the brain. Okay, so I guess most of these topics have been already discussed or in one way or another here. I will talk in the first part of my lecture series, the 3 lectures, will be about mostly the issue of generalization, as you'll see. I'll talk a little bit about learning dynamics, but I won't, the framework will be not about dynamics. So this will be kind of the first 3 lectures, perhaps, and then the last lectures will be about representations and the relations to the brain. To what extent, how we study representations and how you use those tools to relate them to neuroscience data. Okay, so this is the first part. Some of these will be the first part of my lecture series. The first 3 lectures, this will be the last 2 lectures. This all next week. Okay, so that's the plan. So now we're going to, this is a theory of deep learning. Now we can ask what is what statistical mechanics, particular angle, StatMech, on this type of questions. And statistical mechanics has its own way of looking at things. And I just mentioned a few themes in statistical mechanics. For instance, thermodynamic limit. What parameters of the architecture of the network has to go to infinity, or the data has to go to infinity, in what rate, and so on, in order to get something that statistical mechanics can say interesting things about it. So typically, statistical mechanics operates nicely in a thermodynamic limit, not in a small finite systems. How we define thermodynamic limit or limits, perhaps there is more than one in deep networks. Another theme or product of statistical mechanics is order parameters. Some more or less global functions of the entire degrees of freedom of the networks that kind of control or explain the performance of the entire networks, kind of the macroscopic properties of the networks. Coupled with these questions of universality, to what extent there is universality, you can call it typicality, it's the same thing maybe. And then fluctuations around some typical behavior, etc. So these are the conventional themes that statistical mechanics is addressing, and we're now going to ask similar things about deep learning. Scales, scaling relations, power laws, critical points or phase transitions, etc. And finally, in terms of, I would say, tools of statistical mechanics will be like coarse graining, kind of averaging. Fancy tools will be renormalization groups, of course, mean field theories of various types, and numerics. Some statistical mechanics based of numerical tools. Okay, so these are the things that many of those we will touch upon. But that's kind of thing that you expect from a statistical mechanic theory of a system. And this will be true also here. And finally, I want to maybe here, I don't know if you see it. You see it over there here? What are the challenges? Or maybe I write it here. What are the challenges? Why the problem is very hard? And there are a variety of reasons. I just mentioned a few of them. One of them is the complexity of the problem. In many senses. So complexity of the data structure. And I probably don't have to tell you that the old statistical mechanics of learning was focused on very simple data, like Gaussian inputs or random plus minus ones or something like that, and maybe random labels or some simple rules generating the labels. But modern statistical mechanics of deep learning really attempts to be more relevant to machine learning applications and AI and neuroscience. So the data has to be close to reality. So now this is an enormous challenge to generate a statistical mechanic theory for realistic data. The other complexity is the complexity of the architecture, of the network architectures. And again, the old style of statistical mechanics dealt with very simple, mostly either homogeneous looking recurrent networks or single layer networks, or maybe two layer with some committee machine or some simple readout and so on and so forth, with small number of hidden units. These were the types of architectures that we worked on when we did statistical mechanics of learning in the 80s and 90s. But today we really aim to do relevant theory on deep architectures and even more complicated, complex architectures, maybe transformers or LSTMs, etc., etc. Finally, we aim to explain experimental results, like in physics. The theory, first of all, try to explain experimental results and then to predict something new. And for us, experimental results are mostly, there's some neural data, but mostly machine learning application data, empirical data. But the problem is that these empirical data are not necessarily robust. So very often the results are output result of fine-tuning, some kind of engineering, selection of hyperparameters, and so on. So it's not a robust, not necessarily robust, etc., robust properties. So we have to be careful to try to explain real robust properties of networks as opposed to some artifact of very engineered and non-robust results. So that's a danger. So that's among the challenges of any theory, in particular statistical mechanic theory of deep learning. Okay, so that's things that I'm sure you all know about, you heard about. We will discuss them tonight, big questions, etc., etc. So I want to start to do some work, okay? And so this is the background, and now let's start to do some work. So I am going to focus myself in the first part of my lectures on relatively simple architecture, and I'll draw it here. There will be an input layer with dimensions and 0. I'll denote by x the vector of inputs. Then there will be perhaps expansion, not necessarily, but perhaps so, of a few layers up to the top layer, and then a readout weight. And for simplicity today, and I'll focus on one readout output. Okay, so the input is x. It is n dimension and 0. The width of the network, I'll assume for simplicity to be the same, although this is a nice exercise for students to see what happens for the theory that I described if you vary n, or what will be the optimal inhomogeneity in the width. But for now, we'll assume all the widths of the hidden layers are the same, as denoted by n. So now there will be a matrix W1, a matrix W2, etc. So let's call this WL minus 1, and this will be WL, and this will be X. This will be XL, the activation of the top layer, XL. This will be the activation of the previous layer, XL minus 1. So these are vectors, n-dimensional vectors, XL minus 1, the input is X, etc. And then the readout weights I'll denote by A. And then the output will be F. Right? So what is the output? The output, I'll assume a linear readout. So the output will be F of X, a function of the input, and the parameter. So I'll denote by theta the parameters of the system, which is the matrices W and the readout weights vector A. Okay, so this will be a function of this parameter theta, and this will be with the proper scaling that I'll choose 1 over square root of n times sum over I from 1 to n of AI times xi of L, which is a function of the input x and all the weight matrices W. So this is F. Okay, so this is what I'm in here, F of x. Okay, so the readout is the linear, weighted linear summation of the top layer activation XL. Okay, so I is denote the component of the vectors, and X is the input vector. W is the set of all the weight matrices. Okay. Now I'm assuming supervised learning, so I'll have a loss, which depends on of course on the parameters of the network theta and the data d, and this will be MSE loss. So it will be sum over mu from 1 to p. I'll denote by mu the index of the data. P is the size of the data set, and this will be f of x mu, of course a function of theta, minus y mu squared. Okay, y mu, and so the data is a set of pairs x mu, y mu. Mu goes from 1 to p. P, I denote the size of the data, of the training data, the number of examples. Mu is the index. Y is the target label of X. Can be anything, can be real number. It's a real number. Okay, and that's the loss. Okay, so until now everything is fine, right? I mean, there is no problem. Okay, that's a setting of what now, of course, 1/2. We like 1/2 here. All right, good. So now I want to, so what do we do? So we can, of course, turn on learning and gradient descent or some other learning algorithm. I'm not going to do that. I'm going to consider the learning as a process which the output generates a distribution, probability distribution on the weight space, on the parameter space. So this is sometimes is called Bayesian networks or Bayesian learning. So in Bayesian learning, what we looked at, we say what happens after learning is that there is a probability distribution on weight space W, which is induced by the data, and this looks like some normalization, and then exponential, and there will be here minus a parameter which I'll call beta times L times the loss. And then there will be another term which is minus 1/2 to sigma square, and then Frobenius norms of all the Frobenius norms or whatever. This is the trace of all the parameter theta square. Okay, so this means here the simply sum over all the parameters theta I squared from 1 to whatever. Okay, this is this. Okay, so so this is so one can think about it in the Bayesian framework. We can think about it as this is what I'm inducing here. This is the data. This is the loss. This is a regularizer, L2 regularizer. I'm sure again you heard about it. Sigma square is sigma is the strength of the regularizer. This will be important parameter, sigma, strength of the L2 regularizer. And beta is the strength of the loss, or not strength of the loss, strength of the contribution of the loss to the distribution. And this is what we call typically the inverse temperature, and I'll come to that later on. Okay, so again, why we call it Bayesian? Because you can think about it as this part is kind of the likelihood part, and this part is the prior. So this in the Bayesian sense, this is the posterior distribution after training, where so this will be the posterior, and the prior will be of theta will simply be e to the will be Gaussian, e to the minus 1/2 1/2 sigma square times theta square. Okay, so we start with the Gaussian prior on the data or on the parameters, and we modify the distribution given the data. Okay? So everything is fine, right? Okay, good. Okay, so, but now the Bayesian approach is not only describing the learning in this framework, but also what do we do with this? So this is called Bayesian inference. Inference. So in the Bayesian inference, you say, okay, so after I learned, so I have now this new distribution, the posterior distribution, I want to compute things, okay? And typically we'll be interested in, not exclusively, but very often on this, which is called the predictor. What the network, a given network, is telling us, is predicting about the output for given x. X is some arbitrary test point, arbitrary input. It can be one of the training, but typically it's not. So, so the Bayesian inference is, in this case, will be, for instance, we would like to know the statistics of the predictor. So, you know, fx, okay, the average of fx. Okay, so this is the mean of the predictor. So I'm drawing, like in physics, angular brackets for averages. But what I mean by averages here, average with respect to this posterior, with respect to theta, okay? So f of x, the mean of it, is simply given by d theta, d, I mean high dimensional, and then the probability of theta given d, and then f of x and theta. Right? So this will be the mean. Okay, and similarly, we'll be interested in the variance. We can also look at the covariance of the correlation between the predictor at the point x and predictor at the point y. I'll only focus on the simpler quantity, which is simply the variance of the predictor, and this will be simply here d theta p of theta d, and here this will be delta f x theta squared. So by delta f, I mean f minus its average. Delta f is f minus the average. So all averages here are averages with respect to the to the parameter distribution p. Okay, so just definition. Now, why are these interesting? Because they are, I can raise here, I guess, because they are, for instance, the starting point for computing generalization. So generalization will be, in this framework, will be, I'm computing the mean square error of, on a test point x. So this, by this I mean the average of f of x, and again, I won't bother to write every time theta, f of x minus some unknown underlying rule y of x squared. And this can be written as usually as f of x average minus y of x squared plus delta f of x squared average. Okay? So this part is the bias, right? This is the deviation of the mean predictor from the rule, right? So this is the bias. And this part is the variance. And this decomposition is, is very well known in many contexts, including generalization error, the decomposition of the error into a bias term and a variance term. However, one has to, I want to emphasize that this bias variance here are all with respect to the uncertainty about the weights theta, because now there is this distribution. For instance, in a deterministic learning where you get a definite point theta after learning, you don't have that, right? Because there is no uncertainty about theta. Anyway, so this is the bias variance. Now, of course, if you want to compute the global generalization error, the more conventional quantity, this will be average with some probability average over x, over the test point, but typically also average over the data, and then of this epsilon g of x, which depends on data. So this epsilon g, it's not only a function of the test point, it's a local measure, but also a function of the data. So you really have to average over the data and average over the distribution of the test point. Typically, it's in distribution, so the same probability, and this is the conventional generalization error. And of course, you can also write this as a bias and variance, but here the variance include not only this, but also include the variability in the test point and the variability in the data. Okay? Okay, so one more kind of technical point is how do we compute the statistics of the predictor from this formulation? So there is a nice trick. I don't know if you probably have heard about generating functionals here. Has been already discussed. You already know. Good. I see. I don't know what the answers are like this. But okay. Good. So I'll just briefly say, so there is a nice tool from statistical physics to turn partition functions into generating functionals. So we can define a function as ZL, which will be the partition. So Z here is simply the integral over the data, so over the distribution. So this will be d theta times exponential minus beta times the loss, and then a minus 1/2 sigma square. And so this is what we had. So this is just the partition function integrating the unnormalized probability. But now we add here minus IL, a source term, which couples to the predictor. So it will be A transpose X L of X, and of course okay. So this is just the predictor f of X. Right, f of X is just I erase it, but f of X is simply the output of the network on a test point X. So you couple this with a coupling L, and then you have now. So without this is just a partition function. With this, it's going to be a function of the source L, and then it's straightforward to see that when you do this, you get that the mean of f of X can be computed by I times the derivative of the log of Z with respect to L at L equal to 0. And similarly, delta f of X squared can be computed by minus d squared log Z d L squared at L equal to 0. So this is a very, very well-known tricks. And this is why statistical, when you read papers in machine learning, very often say, okay, Z is just, or statistics, Z is just a normalization, okay? But statistical mechanics mostly computing Z, because you can unpack almost everything just by computing the partition function with appropriate additions of sources so that you can take derivatives, appropriate derivatives, and compute all quantities of interest. All right. Okay, so now statistical mechanics of learning is a very similar, actually, almost, I would say almost identical framework, except for kind of interpretation, I would say, which is saying the following. So in statistical mechanics, of learning, we'll say, well, the network parameters have some energy function. Right, so we define an energy function on the network parameters, which again will be function of the data. And this will be, the first term will be the loss, as we already wrote. And then for the prior, we add another term to the energy, which will be T over 2 sigma square times theta squared. And then in a statistic, if I think about the theta, the degrees of freedom of the system, so there is some process which equilibrates the parameters, the degrees of freedom with respect to this energy, and you get Gibbs distribution as equilibrium. So this leads to a Gibbs distribution, which will be P of theta will be z minus 1 times exponential of minus beta times E of theta. Again, I sometimes suppress the data if it's not of interest. Okay, so if you look at this, this is precisely what the Bayesian the Bayesian framework. It's just an equilibrium properties of a stochastic process that equilibrates the weights with respect to this loss function. Okay. Good. So what this process might be, so the many ways to get equilibrium in statistical mechanical systems. One particular, or the simplest one perhaps, is the Langevin dynamics. So Langevin dynamics says that if I think about theta as a dynamical degrees of freedom, and I run obeying this dynamics, so the stochastic differential equations, d theta dt equals to minus the gradient with respect to theta of the cost function plus white noise to 2t times eta. Eta is a vector with the same dimension as theta, and it's white noise. It's just uncorrelated in time and space. Then if you run this, for any given time, if you average over trajectories of this white noise, you get some time-dependent distribution on theta, simply by averaging from some initial condition, running this and up to some time t, and averaging all the trajectories of theta up to this time. But then, and this is a very well-known rule in statistical mechanics, that if you take the limit of t goes to infinity, then this time-dependent distribution generate the Gibbs distribution, generate p of theta, which is what I wrote here, which is the Gibbs distribution. This is this. For any energy, so practically. So this is not specific to this part, but this is just a special case of the energy. Okay, so this is the most direct connection of the Bayesian or StatMech approach to learning to the conventional graded descent approach. You can think about this as what happens if you run a graded descent learning, which is this term, but you add the stochastic noise to it. So the learning dynamics is stochastic. So this is this noise, and then then this stochastic process will generate this equilibrium distribution. But I'll talk mostly about the end result, rather than the details of this, how long it takes, and so on and so forth. Okay? Yes.
Is it trivial to see how this converges to the Gibbs distribution?
To prove this, to prove this is homework, or there is a group of students that are supposed to write this up. I can give references. No, it's not something that it's worthwhile going. I mean, it will take some time to prove. Okay. but it's a well-known old result in statistical physics, so it's not something, it's not about learning. This is general property of equilibrium statistical mechanics. Any energy, any degrees of freedom, if you run these dynamics, well, it's had to be bounded from below, but any normal energy, if you run these dynamics, add this white noise, T here is 1 over beta. This is the relation between T here and beta here, okay? That's classical statistical mechanics, or even quantum, or whatever. But so I just quote it to in the context of learning.
Okay.
Yeah.
Once you say that in general will take exponential time.
It takes exponential time. Exponential in the height of the mountains. I don't know. Exponential time in what exponential? In theta. Okay. Absolutely. Yeah. This is why I prefer not to talk about it. He's talking about exponentials. I hate exponentials. I hide them. Of course, there is a whole story here, right? But what I'm saying is, think about this conceptually as running a gradient descent with stochastic noise, and then you get at equilibrium, you get this Gibbs distribution, which is nothing more than this kind of Bayesian probably posterior. Okay, good. Now I want to add something important, which is the overparameterization and zero temperature limit. So I think I can erase this. No, I need this. I'm sorry. Okay, I need this, but okay. Okay, so what happens if I take the zero temperature limit? And this is the limit which I'll love. I'll focus mostly in the rest of the lectures in this limit, zero temperature limit. Well, you see, zero temperature means infinite beta. As I said, beta is inverse temperature. So if you see, you can look here and see, okay, if beta goes to infinity, if beta is large, we can forget about this. There is no beta here, right? So then it means that the probability will be P of theta, in this case, will be centered at the minimum, at the minimum of the loss. Right? Because this would be the dominator, then beta goes to infinity, then just the theta which minimizes the loss will be, the probability will be sent, and the rest will be zero. Now, typically in many systems you say, okay, this will mean that you go to zero temperature, then you basically pick theta, which is the minimum, the global minimum of the loss. It's unique. Maybe there are some symmetries, so there will be some manifold of solutions, or maybe discrete points, and so on and so forth. This is again, this also, in some sense, in many statistical mechanical systems that we were studying in the past, kind of this. However, we are talking now, imagining a very large network compared to the data. The number of parameters is much larger than the size of the data, and I won't go into the details, but that means that we are talking typically in a regime where there is a whole space of solutions that have zero loss. Yes?
Is it the minimum of L, or is the minimum of the energy function?
But so the energy function, where did I go? Here the energy function. It's a good question. Let's first talk about L and then come to the energy function. Okay? Look at this. Look at this exponential, right? When beta goes to infinity, we don't care about that. So it's just the loss. Okay? But I'll come back to that. Okay? So you just care about the loss and you minimize the loss. But minimizing the loss in the overparameterization regime is more interesting than what you think, because it basically says that there is a whole space of theta which gives you zero loss. which perfectly match the y's with the f, with the predictor on the training data. So then you have, you can think about a huge space of theta, and there is a whole subspace which gives you zero loss, okay? And when you go to zero temperature, you basically focus on this. The rest is zero probability. So you basically sample only this subspace with zero loss. I should use colors, but I hate colors because I'm colorblind. But anyway, but you understand, okay? So now it's different colors. Good. So that's good. But now, typically, actually, this doesn't look like that. It's unbounded subspace. Okay. So if it's unbounded subspace, the probability measure on this, if it is uniform, will not be defined. This is the role of this. In the zero temperature, what happens? You are focusing on this subspace of zero loss, but then you don't sample them uniformly. You sample them with the Gaussian prior, L2 prior. So you bias it to small norm of theta. That's what this is doing at zero temperature. So basically, at zero temperature, the statistical mechanics of learning is giving you statistical properties of the version space or the space of solutions with the L2 regularizer, with the Gaussian measure on this subspace. Okay, so this is how we treat the overparameterization regime. Okay, now you can see I go back to the energy now, because this is what I wanted to happen, because I really want to study the zero error solution space. I put here at the energy, I put T in front of the L2, because then when I multiply by beta, I get constant here, but beta here. That's a matter of choice of parameters. Some different researchers use different parameters, but the way I will scale things is such that that at zero temperature, this is not going to compete with this. It's only going to do the work when this is zero. Then it gives you the proper reasonable measure in the finite temperature. It doesn't matter how you scale. Okay. Good. So far we are good. Now, before we go on to do some work, I mentioned at the beginning a thermodynamic limit. It's already written here. So what can I say about, what are the parameters that we are talking about, and what might be the thermodynamic limit, or what is the thermodynamic limit that I'm thinking about? And the answer for this is that, here, I'll go here, is that there are, okay, what are the parameters, first of all? So the parameters are the data themselves. The data, but more beyond that are parameters like n, p is properties of the data, but still the size of the sample, the width L, the nonlinearity, sigma square, and temperature, sigma and temperature. And then you can ask, okay, so what is a candidate for thermodynamic limit? And I will choose thermodynamic limit to be one in which essentially n and p goes to infinity. But so there is some also n0, but which is the dimensionality of the data. But I'm talking about n and p, the width and the size of the sample of the training data, and then I'll denote by alpha the load, which is p over n, and this will be order 1. I'll keep it order 1. So the ratio is fixed, but n and p are large. So it's a wide network and a lot of data, but the ratios are fixed. L is order 1, sigma is order 1, t's are order 1. They may be small, they may be large, but they don't go with n. So this is the way I scale things with respect to n and define the thermodynamic limit.
I don't understand about n0.
About what?
n0.
N0 is fixed.
Fixed. Okay.
It's fixed. It's fixed. Yeah. The thermodynamic limit is looking at this P and N and the ratio between them. Now, in some cases, I'll come to it, in some cases, you will have to take also N0 to be large when P is large. I'll talk about it later on, but in general, not. In general, you can fix N0 and take N large and P large. And that's good, and that's, again, that's a marked, I would say, change from statistical mechanics, all statistical mechanics of learning. Because we use simple architectures, typically either a single layer, either recurrent or feed-forward, then basically the thermodynamic limit was P and N0, right? But here I'm emphasizing this is different. N0 can be fixed, but the width has to go to infinity. So this is really a different, has different, a very profound, actually, a difference in what we call thermodynamic limit. It's really about, given data, what is the effect of changing the architecture from wide to narrow? All right. Okay, so now we can start to do some more work. And I'll go back to here. Let me erase all this. Erase this, erase this. Yeah.
What is N0?
N0 is the dimensionality of the input.
Oh, okay.
Okay?
Then N is?
What? More questions?
And N?
L is the depth,
Ah.
the number of layers.
Is it the width?
What?
N is the width.
N0. I think she asked about N0, no? Okay, no. Okay, I'm sorry. Okay, N0 is the dimensionality of the input layer.
Yes. And
N is the width, the width of all the hidden layers. L is the depth.
Thank you.
Okay? Okay, so let me go back to here and write down again one more time explicitly what we have here. So what we have here is beta over 2 times sum over the training sets. Mu goes from 1 to P. What we have here explicitly is 1 over square root of N. The predictor on the training data, AI times XI L, which is a function of course, of W, and X, the input, mu, minus Y mu. This is squared. This is the output of the network on the data, the training point, X mu minus Y mu squared. And then here I'll add the minus 1 over 2 sigma square, theta sigma square. But now I want to write this more explicitly. I'll write this, I'll separate two terms. One will be A transpose A, and one will be the rest, W. Okay, so this is our object of interest. So what I'm going to spend a few moments now on something that you already know, I'm sure I have heard during this course several times, but this is what happens if I just fix W and just ask what happens to A, to the readout weight. So W dependent or conditioned, if you want, statistics of A. Okay, that's the first thing that you want to do, because it's easy and it kind of gives you perspective of what to look forward. Okay, so it's really simple, because it is the energy is quadratic in A, right? Here it's quadratic. There's quadratic linear term. Here is quadratic term. So it's basically A is basically Gaussian. Okay. So you collect the quadratic term and the linear terms, and it's easy to compute the mean. And let me just take it, not to make him stop mistakes, to mean and the variance of A. So that's the only thing which are interesting. So the mean of A, again, it's a function of W. It's conditioned on W. I'm fixing W. So the mean of A is sigma square beta times I plus beta sigma square times n minus 1 times XL, I explain what it is, XL transpose inverse n minus 1/2 XL Y. And the fluctuations around this mean, delta A transpose, the covariance matrix of A is simply given by this sigma square times I plus beta sigma square times n minus 1 XL transpose inverse. Okay, so what is this matrix here which I'm taking the inverse? It's very simple. It's the quadratic matrix in this energy function. So the quadratic term A will be the x mu summing over all mu. So this is XL. So XL is a n by p matrix of the activation of the top layer in response to the training data, the training input P. So there will be XLI of X mu. Okay, so this is this XL, this is this matrix, n by P matrix. So this is the contribution of this to the quadratic term. And then the I term is coming from the from this bias, and I scaled out beta and so on. So these are the two contributions to the fluctuations, and then the mean is this inverse times the linear term, and the linear term is simply x times y. So this is xly here, and y is the p pi 1 vector, which is simply y mu, which is the data, which is the labels, target labels. Okay, so again, I don't want to spend more time on this. It's straightforward Gaussian statistics, and you can, again, do the algebra yourself. However, you can actually massage these results, and instead of having inverting this, the inverse has a nice form, and I'll just write the result coming out of this massaging, and this is that A, and I'll skip the W. A, the mean of A is sigma square times n2 minus to the power minus 1/2, and here you will have XL, and again a kernel. Sorry, I apologize. You're already sick of kernels, but what can we do? Times Y, and delta A transpose is sigma square times I minus sigma square n minus 1/2 XL K tilde L minus 1 XL transpose. So you see, I got rid of, well, not altogether. I turned this inverse here into something nicer. Why it's something nicer? So I have to XL I define, right? It's n by p. This is a p by p matrix, p by 1, so that's good, n by 1, and so on. But what is x k? I'm sorry, what is k is the kernel. So k, I first define KL. KL is defined as sigma square times the dot product of XL of the data X, XL of the data X. So capital vector X, by capital vector X, I mean the n by p input vectors. And XL are the activations of each of these inputs. So it is, I'm sorry, this is n0 by p. And this is n by p. So this is basically KL mu nu is sigma square times sum over I from 1 to n, and there is 1 over n here, sorry. 1 over n times x I L of x mu times x I L of x nu. Okay? This is the kernel matrix. Okay? It is basically the dot product, up to this normalization, the dot product of the top layer activation of induced by a pair of input or training data, x mu and x nu. Yeah.
Where did the beta go? It must be either in the...
Where the beta go? Oh, well, I'll come to it. In response to your question, I added tilde. So K tilde L is KL plus T times I. I add a diagonal term to the kernel. So K tilde L is the same KL, but with an additional on the diagonal temperature. So this diagonal, you see the diagonal the identity, I'm sorry, you have to, this is this is n by n because it's acting on A. This is now P by P. So kernels are always, the kernel matrices are P by P, right? Okay, the dot product, so the element of the kernels are top layer dot products of the activation of dot product between the activation of the top layer in response to a pair of inputs. So this is a P by P matrix. Okay, so this is this I. This is an identity matrix P by P. Okay, so this is what you have here. So the inverse now is all in the P by P dimensions rather than in n dimensions here. And the straightforward algebra, nice algebra homework to derive from this to derive this. But this is the form that will inform much of what we'll talk about the rest. Okay. Now, I want to emphasize these kernels here, that's one more. These kernels here are W dependent, right? So because all these activations are for a given W. All what I'm doing here is fixing W and computing the statistics of A in terms of the kernel. Yeah, there was a question here?
That was my question.
Okay, good. Good. This is W-dependent kernels.
So we will assume that in the rest that if you just write the expectation of A, it is the conditional expectation with respect to.
This is conditional W, and then we'll have to do something about it. But for now, I'm just...
Okay.
Okay, good. But now we can also do the statistics on F, right? Because F is linear in A, right? So if I fix W, then I can do everything in terms of the mean of F condition on W is basically linear in the mean of A, and the variance of F is the variance of A. So you get a nice looking expressions for F. So the mean of F is going to be KL, I'll explain to it in a moment, transpose times KL tilde minus 1 times Y, and the variance of F at the point X is going to be KL XX minus KL transpose X times KL tilde minus 1 times KL of X. And you know already what the matrix K tilde is, or the matrix K here. Here, you can define now, you can define KL as a function of arbitrary pair of inputs, where you put here X, well, I don't want to put Y, maybe Y is confusing, X prime, and here you will have X prime. Right, so this will be a general definition of the kernel, Hilbert space, whatever. Okay, so just simply a scalar function, symmetrics dot product form function of for any pair of inputs. And KL, this is a vector. So so this is the kernel now, and I define the vector KL of X to be KL of X of the data and X. So this is the training data, and this is X. So this is a P by 1 vector, where you take the kernel and you put in one of the variables, you put the vector of the training. So if you want, this is KL mu, will be here X mu, and the other variable is the test point X. Okay, so going back to here, the mean predictor, you take this vector KL, it's the kernel of the new data point and the training data. You dot it, you multiply it by the P by P matrix kernel and the data P, and you get, of course, a scalar. And here the variance is interesting because you look at this. This is the naive, I would say, expectation from the fluctuations. It's simply the kernel at the points XX, but you have to subtract the fact that the fluctuations are restricted by the fact that that A has learned, is restricted by the data, so you get the subtraction of that. So this is, take the vector KL, project it or dot it with the matrix inverse KL and multiply by KL. Okay, so this is the amount you subtract from kind of the unlearned part, or the unlearned variance. The total variance would be variance, but the fact that A is learned. Okay, so this is, we'll come back to these expressions again and again in a variety of forms. So you have to internalize this. Okay, the mean predictor and the variance predictor, and how they depend on both the data and the test point X. Good. Now, of course, you can plug it into the generalization error and get what we already discussed. Good. Okay, so any questions until now? So now I want to go, so this is for finite temperature, right? So now I want to go to 0 temperature and ask what happens. So now things start to become interesting, because if we now consider the 0 temperature, limit, we have to consider two different regimes. One which I call the wide regime, and this is when alpha, P over N, is less than 1. Okay, so the width is bigger than the size of the data set. Why this is important? Because then the kernel, when T is 0, this is just K, right? But K is regular only when alpha is less than 1. K has P vectors, it's a P by P matrix, but each one of them is dimension N. So if N is bigger than P, it's fine, it's regular. So the limit 0 temperature is fine. In the 0 temperature limit, we can forget about the tilde here, and etc. And you can see now what this is doing. This actually you can prove easily that this is a projection matrix. This whole thing up to sigma square. It's a projection matrix. No, it is sigma square. It is a projection matrix on the subspace in n dimensions spanned by the input vectors. This whole thing here is a projection matrix on the data subspace. And now you can understand what this is doing. This is simply say that the covariance of A is sigma square, is the prior, minus the dimensionality is minus is in the null space. I minus this will be the projection of A on the null space. And of course, these are the fluctuations, because we are talking about 0 temperatures, so there are A perfectly matches the data, so it means that A is the component of A along the input data are fixed by the learning, and the orthogonal subspace are completely free. So this is the interpretation of that. Okay, And similarly here, if you go to 0 temperature, you just forget about Kate will. And now you see what a sanity check. Suppose I put instead of, I take for X, I take one of the data points. I choose here mu, let's say, the training data. So then this will just be an element of the matrix K. So this will just be Y mu. So this will just give me Y mu. And this is what I expect. I expect that the predictor on the training data at 0 temperature will give me the right answer. And similarly here, if I choose X to be X mu, then this is X mu, this is KL mu mu. This is inverse of that. So this is also KL mu mu. So this cancel. So you get 0. And also you expect this. You expect that the predictor, not the mean predictor, the predictor on the training input will not have fluctuations. Will be 0. The fluctuations will be 0. It won't be Y. So that's the 0 temperature limit in the wide regime. Now in the narrow regime, so this is fine. In the narrow regime, we have to be careful. Alpha is bigger than 1. So as I said, if alpha is bigger than 1, then you cannot simply, with a good conscience, forget about the tilde. Okay? So it turns out that indeed you have to. So for instance, this equation you have to put here pseudo-inverse rather than inverse. Okay? So and similar corrections elsewhere. But it turns out that, okay, if I go back to here, if we focus on the mean predictor, the 0 temperature limit is smooth even in the narrow regime. So in the narrow regime, all the way the theory of statistical mechanics will have some subtleties. So some quantities will not be smooth as you cross this boundary. But many quantities are. For instance, the predictor statistics will be smooth, although you can put your pseudo-inverse. But what I'm saying is the 0 temperature limit will be smooth, and the reason is that you dotted the K to the training data here, and also here, and it turns out that although the kernel is low rank, but it is full rank in the space spanned by the examples themselves, by the n vectors of the training data, and that's fine. Okay, so you have to be slightly more careful when you go to the narrow regime. But it's not fundamental. If you find a temperature, of course, but even 0 temperature, it's not fundamental. But of course, you have to be. I forgot to say, but you have to be. The interpretation now is very different because when alpha is bigger than 1, you have more constraints. P is larger than n. You have more constraints than the dimensionality of the input, which means that when alpha is bigger than 1, this is over-parameterized regime, right? This is over-parameterized regime. L is 0. Here, when alpha is bigger than 1, and remember, I fix W to be some arbitrary W, then in general, L will be bigger than 0, and you will have sometimes unique solutions. So it depends on W. Of course, if you learn W, you can, of course, have 0 loss, and that's what's good about deep learning, even when alpha is bigger than 1. Alpha bigger than 1 is not, P is bigger than the number of parameters of the system. The number of parameters is much larger. But I'm saying if you fix W, and you only learn A, then all what you have is A. So if P is bigger than N, N is the dimensionality of A, then you will typically have a non-zero loss. So you are not in the over-parameterized regime. Now, of course, when you turn on learning, then W will adjust itself so that even when alpha is bigger than 1, L will be 0. So, questions until now?
Yeah, can you just say briefly again why XL K-1 is a projector?
Take this and multiply by XL. Okay? So this is the inverse of that.
This does?
Okay, so if I take this and multiply this part by XL, okay? Then XL transpose XL times sigma square over n minus 1 is just KL.
Yeah.
So this cancels. So you get back this. You get back XL. So it's a projection. If you take X, which is orthogonal, this is 0. So it's a projection.
It's all of it, not just
This part is a projection in the subspace of the data. I minus this is the projection of the null space.
Yeah.
Okay?
Yeah.
Good. The whole thing, including sigma square, the whole thing minus sigma square over n, what I have here, 1/2, I think, XL, KL, minus 1, XL transpose. Yeah. Question? Yeah.
Yeah, so that the variance of the fx goes to 0 at the overparameter test, is this only because it's conditioned on the W?
In the alpha less than 1, it does not, because you mean whether it is 0 for all W or not. I'm saying for yeah, maybe if W is 0, there is some, but for generic W, which is fixed, you can just learn the readout weight.
Okay.
Capacity, right? You ask, I'm sorry. I would look. The masks are similar, what can I say? Okay.
Okay, so if one would leave W free, then one would have some variance over different values.
Yeah, of course. This is the variance. Well, again, no. On the training data, if you don't do silly things and you learn W, and then now the average is average over W itself, it should still be 0, right? Because you learn. Okay, it is 0 temperature, right? But when you fix W and you go to alpha bigger than 1, then you cannot learn A to give you 0 on the training point. Okay, so now we are going to so we understand that's important. Remember this for the rest of your course. And now what we're going to do is integrate out A. Okay, we understand what A is doing as a function of W. We understand what the predictors are doing as a function of, for fixed W. Now we want to do something with W. So the way I'll deal with W, I'm looking at I'm marginalizing A. So I'm taking P of W to be dA, integral dA, P of A and W. I'm integrating out A, okay? But that's not difficult because it's, again, integrate out quadratic, Gaussian A. So you can just do it. Homework? No, it's not even homework. Okay, so what you find, here it is. So what you find is that this is Z minus 1, and then you get E, you get minus 1/2 Y transpose K tilde inverse Y. You get minus 1/2 log determinant of K tilde, and you get minus 1/2 sigma square trace of W square, the prior of the bias. This is what you have, okay? So it's nice. So, well, I think it's nice. So the way you can think about it again is that this is inducing a Hamiltonian on W. So you can write this P of W like Z inverse times exponential minus H. I call it Hamiltonian. I don't write it beta. I absorb beta in it. So this is the new action or energy function on W, which is just given by, so HL of W now has several terms. 1/2 Y transpose K tilde inverse Y. Okay, that can be, I erased it, but you can see from what I already described that this is simply A transpose A, average. and then you have minus 1/2 log determinant of k twiddle. This is kind of entropic term. So this is nice. This is coming. This is essentially A, more precisely A transpose A. The mean of A with respect to W for fixed W. Yeah. The norm of the mean of A squared is coming here. So this is a relic. This is a relic of this term. Okay? And then this is kind of the entropic term which is induced by A, marginalizing over A, log determinant K tilde. And then there is the prior regularization. So it's kind of, interesting interpretation of what these terms are doing. Okay, and then this one, and then I have this one, minus 1/2, minus 1/2 sigma square, W squared. So again, so basically what I'm saying, we get rid of W, we get rid of A, and then the rest of the work we have to do is dealing with the marginal measure on W.
Does the signs upper root be the opposite?
This is plus, and this is plus, yeah, thank you.
The first and third terms here seem very easy to interpret.
What?
The first and third terms of H of L, or H sub L, seem very easy to interpret. Can you give an interpretation to the log to determinant term? It feels like it's sort of. So this so this is W. Yeah.
Now, okay, I erased this. So if you remember, I had A for given W to be 1 over square root of n times X L times K inverse minus 1 times Y, more or less. Times sigma square times sigma square. So you can, if I take this and dot it with itself, then I get again K X transpose. So I get Y transpose K inverse minus 1 times K itself times Y. And you have to do massaging with temperature and so on. You get this. You can work it out. This is basically representing the amplitude of the readout weight. Okay. Now that's very important because it means that the amplitude of the we're talking about L2 as inductive bias, and a very important role here. The norm of the W, of the A's are the ones which are inducing the data-dependent term constraint on W, which is this one. Particularly Y. You see here, Y doesn't appear. This only depends on the inputs. This is the only term which depends on Y, on the target, let me say. And this is the usual bias. Okay. You don't have to believe me. You can look at the paper. We can work it out the details. But so what I'm saying, there's some interpretation of this. It's induced by the norm of A, induced by the entropic subspace space of A, and by the variance of it. But the fact that we can give it names and interpret doesn't mean that it's simple. It is horrible, right? Because this is a very nonlinear function of W. Remember, K is a function of W, Kn. And this is the inverse of K. So everything here is horrible functions of W. So, you wonder what you can do with this. You can give it names, entropy. Okay, good. So this is, to me, statistical mechanics of learning is doing something with this Hamiltonian. This is statistical mechanics of learning. All right. Okay. So what we can do is the following. So since we are desperate to do something with this horrible nonlinear function, we use what we can do. We hold to whatever trick that we have in our bag, and the simplest trick is to take the infinite width limit. So that's what I'm going to do now. As a first move will be the infinite width limit. It's also called its equivalent or similar, depending on up to some caveats to what is known as the Gaussian process limit or neural network Gaussian process limit. And this is something that Yasaman and maybe also Boris will talk extensively about in their lecture. So I will just give you the perspective of statistical mechanics, but I'll leave the details of how you really calculate things in this limit to them. All right, so in that limit, again, I'm not going to do, I'm going to wave my hands because you can do more serious work and say, well, look at this Hamiltonian. This is in W. This is, what is the order of this? Can one tell me? Order of magnitude, how this scales with N and P and whatever L. Well, this will be n squared times L more or less, right? Times n0, right? So this is even for L equals to 1, this is just n squared, right? What will be the order of this? Julia, you already started. What? Log determinant of a P by P matrix. What? It's a log of the determinant of a P by P matrix. P, order P. This is also trace, this is also P. So these are order P and this is order n squared, okay? So if we take the limit, so what we mean by infinite width limit, we say n goes to infinity, but P is finite, okay? So you can show more rigorously, but I'm just waving my hands for the lack of time, that these terms are negligible. So the Hamiltonian induced on W is just the prior. Gaussian prior, that's W. Okay? So this is what it means, the infinite width limit or the Gaussian process limit. So step number 1, result number 1, is that HL of W is simply Gaussian, 1 over 2 sigma square W square. That's step number 1. But step number 2, that's even more fun, is that to compute, this is still, quantities like predictor is the inverse of the kernel and so on. So it's, again, horrible function of these Gaussians. But it turns out that things are simpler in this limit, even in that sense, in the sense that what I'm claiming is that any function of W, which is not a function of W directly, but a function, let's say, any function of W through the kernel, if the function is a function of W, some complicated function of the kernel, is self-averaging, which means I can replace this by f of the average of the kernel with respect to W. And then the average here is with respect to the Gaussian W. Okay? So that's a normal simplification. I don't have to worry about averaging the inverse and so on and so forth, because I just average the kernel themselves and then take it. So that's known as self-averaging or concentration in statistics or in statistical mechanics. And basically the reason is that the kernel itself is centered. The fluctuations in the kernels are negligible. This is why you can neglect the fluctuations in the kernel. Okay, so again, I don't know if this had been discussed already in the talks here. No, okay, so let me just do it briefly. So what is the kernel? KL, I'll remind you what it is. It's sigma square over n times sum over I from 1 to n of, let's say, KL xy, x prime. Two pair of inputs, right? So this is going to be sigma square over n times x. But what is xl? This is phi, the nonlinear function, of WLI dotted with xl minus 1, which is a function of the input x, and then another phi, which is WLI dotted with xl minus 1 I, no, not I, this dot product, L minus 1 of x prime. Right? This is the product of activation of the neuron. This is x Li, what I write here, in response to x, and this is xli in response to x prime. Right? Is it clear? I'm just using the feed-forward structure. Okay. So now let's fix WL minus 1 and the rest. Let's just focus on the WL matrix, only WL matrix. So these are the set of vectors, right? So this is WLI. So this is my top layer, and I have these vectors. So this is I. This is WLI. This is WLI, right? This is L minus 1. The activation at L minus 1, and dotted with WI. Okay, and the same WI, because I'm looking in the kernel, I'm looking at the same neuron in response to a pair of inputs, and I'm multiplying them, and then sum over all I. Okay, that's clear? All right. So now the point is that these vectors, WLI, if I look at this vector, which is WJ, let's say, these vectors are independent, are Gaussian independent, are IID. So this vector and this vector are independent. So you have infinite sum of random of functions of this independent random variable Wi. So in the large n limit, you can just forget it, forget the sum, and just replace it by the average. So in the large n limit, this will be sigma square times the average of phi of W. Let me drop the L. WL, WI transpose XL minus 1 of X times phi of, I'm sorry, there is also square root of n inside, because that's the way we normalize all the pre-activations. So there is square root of n here, and then here WI transpose X L minus 1 X prime, and again normalized by square root of n, phi, and then average. And this average is respect to the vector, to the Gaussian vector Wi. Okay? A condition on the rest of the W's.
Yeah, so we consider them at initialization. We didn't learn.
There is no, okay, good question. Forget about initialization. That's not anti-case. There is no dynamics. It's all equilibrium. I don't care. There is no memory of initial condition. Remember, Gibbs distribution. We started with Langevin dynamics. You start from initial condition. You forgot about initial condition because you equilibrate. So we're all talking about equilibrium. There is no notion of initial condition. It just, this is not initial condition. It's just a Gaussian measure on W at equilibrium.
Okay, so this is a question now. If I start with two random initialization, right, in this regime,
Nothing. It
do
will.
you converge to the empirically? Do you converge to the same point or not? Or do you converge?
If I run the Langevin dynamics, I don't convert to the same point. Convert to the same distribution.
Yeah, do you converge to the same distribution?
Of course, the distribution is ergodic. The system is ergodic. That's a theorem in statistical mechanics. Well, in practice, depends how patient you are. No, I'm serious. We are patient, and we do get this result. Or if you're not patient, you average of initial conditions. Technicalities. Physicists don't like to talk about technicalities. Okay, more questions.
I don't completely understand why at infinite the W for different channels are independent.
Why these are independent? Because actually each element in W is independent. They are all IID Gaussians. Each element of these are IID. So in particular, this vector and these vectors are uncorrelated. Remember, this is gone. This is gone. We only have this.
Okay, this limit. Okay.
That's it. Gaussian prior.
And what is the function phi?
Phi is the nonlinearity. You remember, each neuron Each neuron at each layer, X at each layer L is phi of W, let's say layer L and neuron I is phi of L I, the vector I dotted with the previous layer, XL minus 1, and then normalized by 1 over square root of n. That's the model. I should have said it, but okay, that's the model. Okay, more questions? Yes? Oh, wait, but but there was a question here. Yes.
Should we not be scaling sigma or sigma squared with n in some
way? No. There is lazy, not like, no. I'm doing simple-minded statistical mechanics. This is the scaling. Sigma order 1, T order 1, L order 1.
But it feels very weird then that we have this n by n weight matrix with weights that are order 1. Is this not strange?
Can you say it again?
Like, so then each weight is order 1.
Each weight is order sigma square, or sigma, yeah.
Right.
Yeah, each weight is order sigma, and therefore, okay, so I didn't want to spend time with it because I thought that maybe Yasaman talked about it, I mean, somebody else, or maybe she'll talk about it in more detail. But I want to tell you, this is a very, it's not the only normalization possible, scaling possible, but it's a very generic or intuitive choice of scaling because it really means, again, in this over-parameterization regime, that the signal will not be order n. Even after training of W, this signal would still not be order n, there are n terms here, will be order square root of n, and therefore you normalize by 1 over square root of n. Now, if in some cases, depending how you will normalize it, if I put n here, then it will force the learning to be much more drastic in order for this to be order n. So I'm not doing it. So again, we can schmooze about it over beer or something. It's an important issue. I just said, well, this is the scaling that I'm choosing. But it's not the only one. But the other ones are harder in some sense. The other one are from the beginning, take W or take all the weights and give them a hard kick because they really have to generate a very strong signal to compensate for the 1 over n. Okay, more questions? Yeah, you had the question.
Okay,
Okay. So we can, okay, lunchtime. Okay, good. Okay, so I'm almost done because you see, these are, okay, so now I can forget about the summation 1 over n, and I just have this one. But furthermore, what is this one? This one is just, you know, W is Gaussian, X is fixed, this is fixed, all the W's are fixed, but Wi, these Wi's are Gaussians. So you know, sum of Gaussians is Gaussian, so this is just a Gaussian. And this is another Gaussian, so I can write this as sigma square times average of a scalar Gaussian Z and another Gaussian Z prime, an average over Z and Z prime, two Gaussians which are correlated. And it's easy to write down the covariance matrix of Z. So Z square, again, I fix W, so Z square I just average over W. Each independent component is random. So I sum here, I just get X squared by itself with sigma square. So this should just be sigma square 1 over n times X L minus 1 of X dotted with X L minus 1 of X, right? Because I'm taking Z squared. This is Z, and I'm squaring it. So I just get this dot product with itself, and the sigma square coming from the variance of W, and 1 over n coming from the square root of n squaring. So this is basically nothing but, what is this? Dot product of the XL minus 1. What is this? It's what? The kernel at the lower level, right? So this is simply KL minus 1 of XX. My notation, I'm trying to be consistent. The variables of the kernel. The kernel is a function of a pair of input vectors. So they're defined in input space, right? So this is, but this is the activation at the L-1 layer due to the input X, and this is by itself, because just square this and average, right? So I get this. And similarly, Z prime squared will be the same story, will be the activation of L-1 X prime, X prime. It is squaring this and averaging over W. And then finally, they are correlated. So if I look at Z prime, the correlation between them will be to take this and to multiply by this and to average. So W are matching, and then I have the product, the dot product of this with this. So this will just be KL minus 1 of X and X prime. Which is still, of course, all this N minus 1 depend on the lower W's. I average the top layer. Okay? So what do I get? Very nice thing. I get that the kernel KL in this GP limit, so I get that the kernel KL of X and X prime is, I replace it by its averaged. So it's average KL of X and X prime. And all the average that I've done so far is average of a WL. This is the top layer W. And what I got, it is a function, it is this, right? And this is, you know, you have to work hard to compute it in general, but it is a scalar function of a Gaussian variable Z times the same function, nonlinear function of another Gaussian variable Z prime with these variances and covariances. So I don't care. You have to work, you know, two-dimensional integral to do. You have to work hard. I don't like to work hard. So I write it as, and I have sigma square here, fine. So I write it as sigma square times this quantity. So it will be times F, which is a function of the variances and the covariances. So it will be a function of KL minus 1 XX and a function of KL minus 1 X prime, and a function of KL minus 1 X and X prime, the cross term. Some nonlinear function which is coming out of integrating this two-dimensional, doing this two-dimensional integral over this two-dimensional Gaussian, Z and Z prime, which are correlated. So this is F. Okay, good. But now you see that now I have to calculate this. But with the same argument, I write KL minus 1 in this fashion, and I do the same thing. So they are going to be then functions of the lower level case, and so on. So you can iterate it until you get to the first layer, where by integrating W1, you get the input kernel. So by this iteration, even at the end, if you average KL of X and X prime on all W, on all layers, what you get is maybe horrible, but you get a nonlinear function, which depends, of course, among other things on L, which will be only a function of the input kernel, K0 XX, K0 X prime, and K0 X and X prime, where K0 of X and X prime is simply the dot product normalized of the input vector, X dot X prime. And 0, thanks, and 0. Because the normalization of the pre-activation at the first layer has to have n0, square root of n0 rather than square root of n. So that's the end of the story. That the problem is solved because, you know, for instance, if I'm interested about the mean predictor, the variance of the predictor, the covariance of the predictor, and so on and so forth, all that I have there already shown that I have kernels, W-dependent kernels. But now I'm telling you, each kernel, you know, you have k, you have inverse k. Each kernel term, you just self-average it and replace it by the Gaussian process kernel. So just to summarize, if you want to know the mean predictor in this limit, okay, so the mean predictor will be f of x in this infinite width limit, which is called the GP limit, will just be what we had before, k L of x, but now computed in the GP limit, k twiddle. I just add GP limit here, inverse and y. And similarly, the fluctuations will just be replacing every time you see a kernel, you replace it by, so we have here k L GP XX, and you have minus k L transpose x, k twiddle L GP inverse k L of x GP, and so on. So the only thing is, what remains is to compute those kernels, the Gaussian process kernels, and there are cases where they're very elegant and nice, and Yasaman will talk about them, and there are cases that are hard, or you have to do some numerics, but in any case, that's it. And similarly, other quantities of interest, everything you replace, the trick is replace everything, translate everything in terms of kernels, and once you have kernels, you know how to deal with them. Okay, and I want to close, because I have to close, by just saying it's very nice and simple, problem solved. What is wrong about it? So I just want to say a few words, very quick words about the limitations. The limitations of this GP limit. First of all, maybe the most important one is, to my view, is unrealistic. Because you really have to, if you want to apply it, to see whether it applies to a large network with a very small number of examples. It's not realistic. But it also doesn't give you much. Because, for instance, it does not tell you the role of overparameterization, in the sense that you cannot vary it. You just get infinite. You are stuck in the deep overparameterized regime because n is infinite. So you don't know what happens if you go near the interpolation threshold away from it. There is nothing to, this is basically the same as saying, what is the role of the width? There is no role because you take it to infinity. So you cannot address these questions. And finally, related to it, no representation learning. There is no learning of representation, because representation, I mean, what happened to the hidden layer representation, but they are just Gaussian. There is no effect of learning on them. Only the top layer, only the readout has learned. The rest are Gaussian, so nothing to say about representation. And the final point is, and again, Yasaman will talk about it, there is some pathology in the L goes to infinity limit. Kernels may diverge, may go to some uninteresting thing, and so on and so forth. So you cannot really push it to a very deep network. Very deep networks will fail if you work in this Gaussian process. Okay.